First, we draw Mars as a circle with the prime meridian on the bottom. You can picture this as a top-down view as there are only 2 dimensions. Then we draw Olympus Mons relative to the prime meridian. Olympus Mons has a longitude of 133.8 degrees. Split the circle in 2 so that the west side represents night and the east side represents day. Given that we are trying to find the proportion from the prime meridian to Olympus Mons in hours, it is important to acknowledge that each side takes half of a Martian sol to fully rotate. If the location is on the west, it has a negative time delay, and if it is on the east, it has a positive time delay. Olympus Mons is on the west, and thus has a negative time delay. We can calculate this delay by finding the proportion it is into the half circle, longitude divided by 180. Then multiplying the result by half the Martian hours in a sol. Gives us a delay of 8.92 hours, or negative 8 hours and 55 minutes and 12 seconds. This means that the time on Olympus Mons is 15 hours and 15 minutes and 48 seconds when it is midnight at the prime meridian. We would be done by now if we were only calculating the delay between Olympus Mons and the prime meridian, but I want to be able to calculate any delay, not just Olympus Mons and the prime meridian. The way we do that is by first writing down a general formula and then substituting longitude values for it. It works even if the longitude is 180 degrees and it is either positive or negative, because the result of either subtracting or adding a delay of 12 will always be equal. You can test this if you like. Naturally, trying to find the time delay between the prime meridian and the prime meridian will give you positive and negative 0. But wait, 0 isn't a quantifiable amount, so how can we assign direction to it? Well, we can't. If you were to travel 0 degrees east or travel 0 degrees west, that would be exactly the same thing because you didn't move at all. Okay, bye.